for a nice introduction.
Thank you, sir. Thank you.
Warm
Please
greetings.
continue, sir.
Yes, sir. Warm greetings to everyone. Myself, Dr. V. Nandala, Professor, EC Department, Sri Krishna College of Engineering Technology. I'm in this field for a decade, and I have created a few scholars in this antenna and RF engineering domain. With based on the research what we carried out recently for the 6G networks, that is what I'm going to deliver out today. So it is a real engineering what we discovered in material selection of 6G, and how do we can go with material selection and substrate selection with respect to patch and with respect to substrate. We have did a lot of research, and we have created a lot of Q&A journals recently. Based on the inference insights I'm going to present right now. Yes. My topic today is overview of 6G networks as a spectrum's scarcity perspective. Overview of 6G network. My presentation outline will be as follows: introduction 6G networks, spectrum scarcity challenge and technological solution, need of Tera band and its futures, use cases and application, conclusion and references. Yes. What is introduction to 6G networks? What is 6G? The sixth generation of wireless communication technology, expected to provide faster rates, lower latency, and more reliable connection compared to 5G. As we all know, we are migrating to higher data rate speed. That's why we moving forward from 5G to 6G. Now, right now we are using sub 6 gigahertz frequency 5G service only. So our future emerging technology, due to spectrum scarcity, we are moving on to the research of 6G networks. The key features of 6G, it speeds up to 1 terabits per second, millimeter wave, and it will be sub terahertz and terahertz frequencies will be using. Advanced AI and machine learning integration will be done in 6G to improvise its network performance in the upcoming era. Introduction to 6G networks. 6G represents next generation of wireless communication technology. It promises to revolutionize connectivity with unprecedented speed and capacity and latency. Limitations of current 5G networks, as we all know, it is of limited bandwidth, high latency, energy consumption, and coverage, network coverage. So by emerging 6G technology, we can fulfill all the drawbacks of 5G by using terahertz communication. The spectrum scarcity will be reduced, and using AI algorithms in network performance will be enhanced in 6G compared to 5G. And holographic beamforming, it is a concurrent transmission of signals using the same frequency. With that, the interference also will be reduced. It is an emerging beamforming technique. With that, we can go with 6G to have a better network performance. And satellite networks, by using 6G communication, interlinking to satellite communication and improving the terrestrial networks, we can expand our service to even remote villages with a good speed of delivery and quality. And quantum communication, it is yet another upcoming field where we can use 6G technology for getting faster transmission and good quality signal delivery and reliability. And key performance indicators of 6G, as compared to 5G, we are right now using 20 gigabits per second, and 6G we can expect up to 1 terabits per second data rate, and latency for 5G 1 millisecond, and for 6G 0.1 millisecond. Connectivity density, as for 5G, it is 1 million devices per kilometer square, and for 6G it is 10 million devices per kilometer square. That much devices we can add on. Energy efficiency, it is moderate in 5G, and it is highly efficient when you go for 6G. These are the comparatives with respect to the key parameters of peak data rate, latency, connectivity, and energy efficiency in between 5G and 6G technologies. Potential use cases and applications. Using 6G, we can have a better smart city development. 6G will power interconnected smart city infrastructure, optimizing transportation, energy management, and public safety. And industrial automation can be enhanced, and robotic machine, automatic automation of manufacturing and logistics will be carried out in a better way by using the 6G technology. Healthcare, it plays a major role in healthcare also. We can go for remote surgery, telemedicine, and wearable healthcare devices. With using that, we can do the patient monitoring. That is what we name it as always. The IEEE standards, we mentioned the Targa Mantra, advancing technology towards humanity. 6G, in upcoming era, and 6G will come up with all the desirable needs of human. With that, we can enhance the medical facilities. Challenges and obstacles in 6G and 6G deployment. We'll have spectrum availability. Securing sufficient spectrum for 6G deployment is a major challenge. So the infrastructure building to build up 6G, it is an upcoming challenge. Device compatibility. So what the device right now we're using, we have to make it compatible to 6G standards and protocols, and that will be a quite challenge. And infrastructure cost. So build up an infrastructure to come arrive with 6G networks. It is the upcoming challenges in 6G. 6G network architecture infrastructure and cloud native architecture. 6G will leverage cloud computing for dynamic resource allocation and scalability, and software defined networking. SDN enables flexible network management and automation, optimizing performance and resource utilization. Edge computing is an upcoming field. Edge computing brings data processing closer to users, reducing latency and improving response times. Massive MIMO, multiple input, multiple output antennas. So this will enable the good transmission, and it will improve the coverage region. It will be embedded with 6G. 6G spectrum and frequency allocation. In terahertz spectrum, we will use from 0.1 terahertz to 10 terahertz. That is the bandwidth we upcoming 6G we can preferably use. We will use dynamic spectrum allocation, and we'll be using dynamic spectrum allocation for doing the 6G communication. Here we'll have a scenario for representing 6G networks. And security and privacy consideration. When we go for upgradation of 5G to 6G, these are the constraints taken into account: data encryption, authentication, data privacy. The future wireless communication, 6G and beyond. So beyond 6G, we will end up with 7G in the future upcoming eras. And key technologies enabling 6G. Using 6G, we can in upcoming 6G network, we'll use a lot of AI algorithms for enhancing the performance of network, and we'll have a good security features can be established by using AI algorithm. So we'll have surely we'll have an integration of AI algorithms with enhancing the network performance of 6G. That is one another area of emerging research, and massive MIMO technology will be used for improving 6G communication. Terahertz frequencies will migrate from right now we have a frequency range of 24 gigahertz frequency set. Sub gigahertz, 6 gigahertz frequency. Right now we are using 5G standard is sub gigahertz frequency. It is from 3 to 6 gigahertz, but the future 5G network, it will be 24 gigahertz to up to 40 gigahertz, and 6G it will start from 0.1 terahertz to 10 terahertz. Potential use cases for 6G, immersive experience, autonomous vehicles, smart cities, and IoT, healthcare, and advancement. These are the major tasks that will be using 6G in upcoming era. Challenges in developing 6G, as already we discussed, technical complexity, spectrum availability, standardization, and interoperability, cost and investment. These are the upcoming challenges. Global efforts in 6G research and development. Academic researchers doing a lot of research in 6G technologies, and industry collaborative upbringing with respect to industry automation. They're doing a lot of research in 6G. Government initiatives also, Indian government also, they have started with doing research in 6G and international standards, IEEE standards. They're improving a lot of protocols for 6G networks. So timeline roadmap for 6G deployment, 2020 to 2025, research and development phase, focusing on key technology, proof of concept, demonstration, and initial standard development for 6G. 2025 to 2030, it is a pilot deployment and trials in specific application regions, refining technology and gathering real-world data. 2030 and beyond, wider commercial deployment of 6G network with technology become increasingly ubiquitous and integrated into daily life. Smart antennas revolution is in 6G networks. Smart antennas, as we know, reconfigurable antenna, and we have a lot of frequency selective surface antennas, and we have splittering resonator antennas. All different technologies will imply in smart antenna to have better enhanced performance of smart antenna in 6G. Okay. The as we all know, directional and omnidirectional antennas. Smart antennas will be more directive. With that, we can have a good performance, enhanced performance as compared to normal omnidirectional antennas. And beamforming techniques, we'll have a digital beamforming, analog beamforming, and hybrid. It involves the combination of digital and analog beamforming. So these, as we already know, are adaptive array processing algorithms, least mean square, recursive least mean square, constant module algorithms. These are the present trend algorithms used for signal processing in smart antennas. Advantages of smart antennas in 6G: increased capacity, improved coverage, and enhanced security. Challenges in implementing smart antennas: high complexity, power consumption, interference management. So the power consumption of smart antennas plays a major role right now. A lot of people doing research in power consumption of smart antenna using convex concave optimization tools and high complexity hardware beamforming. Also, they are doing a lot of research in respect to beamforming. Interference management, that is signal processing related techniques. Also, they are doing a lot of research in this three wider area. A lot of people doing research in for the 6G and 5G networks. Interference mitigation using smart antennas, null steering, spatial filtering, interference cancellation, which will be deployed for reducing interference in smart antennas. Capacity and coverage enhancement with smart antennas, increased data rate, extended coverage, enhanced connectivity. Now, standardization efforts for smart antennas in 6G. Here we'll have a 3G generation partnership project. Seeing some noise disturbance. So 3G partnership project and IEEE standards. They have the P team. They will come arrive with a lot of standards for developing 6G networks. And future trend and research in research directions in 6G is based on MIMO technology, intelligent reflecting surface, and reconfigurable antennas, and pushing the boundaries of smart antenna technologies. Next, this is the place where I want to start with. Previously, I given just introduction about the 6G antenna, 6G network perspectives. What are the advantages and drawbacks of 5G, and what are the advantages of 6G? How do we can enhance 6G performance using AI? And what are the different modulation techniques we can apply for getting a better 6G network? We have discussed. This is the point where we did our research. We have carried out our research. The spectrum scarcity challenge. The definition of spectrum scarcity, it represents defines limited availability of radio frequency spectrum due to high. The spectrum scarcity is nothing but it is a limited availability of radio frequency spectrum due to high demand. Why spectrum scarcity matters for 6G? 6G it provides a huge bandwidth for deploying smart environment and have a better enhanced speed, data rate, and security, and reliability, and faster data transfer. And to have a better world, real-time world, we can go with a 6G. Increased data traffic and demand, high bandwidth can be given by it can be utilized by using a 6G network. Frequency spectrum overview. Current spectrum allocation for 5G in lower band it is less than 1 GHz, mid band 1 to 6 GHz. Right now, what we are using as a 5G it is nothing but sub 6 GHz frequency, where our recent 5G services uses only this mid band, and high band it is greater than 24 GHz and limited to 40 GHz. Proposed spectrum for 6G expansion into sub terahertz and terahertz band. So 0.1 terahertz to 10 terahertz, that is the proposed spectrum for 6G. Technological solutions to spectrum scarcity. Using terahertz band considered as a major solution. To tackle spectrum scarcity, the research focuses on exploring the opportunities in terahertz band, a relatively less explored frequency range. Spectrum sharing, dynamic spectrum access, allowing multiple users to share the same spectrum band. Cognitive radios, smart radios that can sense and adapt to the spectrum environment. Reconfigurable intelligent surfaces that can control automatic waves to optimize signal paths. Introduction to automatic spectrum. The automatic spectrum is one of the most strictly regulated and expensive resources. Access to radio spectrum is crucial to the function of all mobile devices, whose number is drastically increasing every year. In order to accommodate many mobile user, adoption of efficient spectrum use technology have evolved address and the challenges of interference and spectrum scarcity. To tackle spectrum scarcity, the research focused on exploring opportunities in terahertz band, a relatively less explored frequency range. So here with we have a terahertz band. It starts from 10 power 11 to 10 power 13 hertz frequency. So it from 100 gigahertz to up to 10 terahertz. Terahertz in terahertz and other high frequency waves. Millimeter wave, it ranges millimeter wave where the frequency spectrum ranges from 30 gigahertz to 300 gigahertz. And we are, for commercial application, millimeter waves will use 24 gigahertz to 80 gigahertz. Infrared, it is 10 terahertz to 430 terahertz. It uses low penetration of power. Visible light communication, it is 430 terahertz to 7900 terahertz. Need of line of sight between transmitter and receiver suitable for short communication. Ultraviolet frequency ranges from 790 terahertz to 30. Health, it introduces health hazards. And now we get into terahertz frequency, terahertz wave frequency range. Frequencies ranges from 100 gigahertz to 10 terahertz in wavelength 3 millimeter to 300 millimeters. And energy, temperature, ionization, it is a non-ionized wave propagation. Potential potentials of potential of terahertz waves. It will have high directivity, excellent spatial resolution, high penetration power. It is a non-ionizing radiation, high imaging capabilities, and the application of terahertz waves. It is nanoscale application, mobile access, precision medicine, on-chip connectivity, monitoring of plant growth, microwave application, Gertrude detection, explosive detection, gas sensing, information sharing, air quality detection, and positioning. And various terahertz wave application, terahertz wave communication application. We can use in astronomy IEEE standards, EMC, database measurements, superconductive electronics, and we can go for non-linear biometrics, sensors, optical communication. In various fields, we can use terahertz communication. That is what we are given a detailed diagram, networking to various fields. And key challenges in utilizing terahertz band, antenna design, adapting traditional microwave antennas, high absorption in moisture, proper modeling and design procedures, electromagnetic interference and compatibility, line of sight requirement, complex signal processing, interoperability. So in introduction to terahertz antenna, it is a metallic antenna suitable for simple and cost-effective designs. Dielectric antenna preferred for miniaturization and impedance matching needs. Metamaterial antennas offer potential for significant performance breakthroughs. And types of terahertz antennas: terahertz photoconductive antennas, terahertz horn antennas, terahertz lens antennas, terahertz on-chip antennas, terahertz microstrip antennas. Right now we have a tabulation and we'll have the advantages, disadvantages of various terahertz antennas types. Terahertz photoconductive antennas, advantages: excel in generating terahertz radiation. Disadvantages: poor photoelectric conversion efficiency. Terahertz and horn antennas, better directivity, excellent gain and compatibility with waveguides, large range size. That's a drawback. Terahertz lens antennas, easy in integration with the planar circuits and better performance. Disadvantages of terahertz lens antennas: complex design and very expensive. Terahertz on-chip antennas, it is scalability and cost effectiveness. And disadvantages of on-chip terahertz on-chip antenna: fabrication complexity. Terahertz microchip antennas, small in size and low cost. And disadvantages: narrow bandwidth and poor performance. Methods to improve the performance of microstrip antennas in the terahertz band. Here we have parameters to improve the performance of microstrip antenna in terahertz band. Based on this, here I have listed 10 different parameters to improvise the terahertz antenna performance. Where in these 10 parameters, we have selected in our research, we have selected three parameters, and we have did our research in terahertz antenna communication using high frequency structural simulator. We have designed antenna with respect to three key parameters, that is material selection, frequency selective surface, and split triangle resonator. Based on these three parameters, we have done our designed our terahertz antenna, and we tested, and we have end up with some inference on the design of antennas. So we have a huge scope of doing research in this with respect to this 10 types of key parameter, where in which you can do a lot of research in terahertz antenna design, and we can do a lot of quality publications also. So methods to improve the terahertz antenna terahertz antenna communication, you can go with better material selection and photonic band gap structures, grating structure, dielectric substrate, slot coupling, antenna arrays, frequency selective surfaces, tapered slot antennas, near field coupling, and split ring resonators. In our proposed research, we have selected different materials for terahertz antenna. And for the material, in the sense, we have selected three different materials of patch radiating element, and five different different substrate material for terahertz antenna design. With that, we have derived some inference. Similarly, we have tried out with one more terahertz antenna design, where we implemented frequency selective surface, where we have simulated, and we come arrive with some inferences about terahertz wave antenna performance. And similarly, we have did our research in designing a terahertz antenna, with where in which we used a split ring resonator, and we derived the performance parameters of terahertz antenna. So the first one we selected material selection, and the second one we selected frequency selective surface parameter, and the third one we selected split ring resonator. In our research, for the first one, we designed a terahertz antenna, where we used different material selection in terms of patch radiating antenna and substrate material. We have selected different materials with based on the different combos. We have derived the antenna key radiating parameters in terms of return loss, VSWR, gain, efficiency, bandwidth, everything we derived. Then we come arrive with the right material selection for doing for fabricating a terahertz antenna. Similarly, in the first material selection, we have designed a terahertz antenna with a frequency range of 0.3 terahertz. And in the second proposed research, we have selected frequency selective surface terahertz antenna, where we use a frequency range of 1.5 terahertz. And for the third proposed research work, we selected split ring resonator terahertz antenna, and where we use the frequency of 1 terahertz. So we have used three different frequencies. With respect to material selection, we have designed a terahertz antenna of 0.3 terahertz frequency, and frequency selective surface, where we designed the antenna with operating frequency of 1.5 terahertz, and third one split ring resonator, where we designed an antenna of operating with a frequency range of 1 terahertz. And based on this three key parameters, we extend our research of designing a terahertz antenna, and we come arrive with some inferences. That is what we are going to display right now. Methods to improve the performance of microstrip antennas in terahertz band. So here we have different techniques of material selection, and we have the proposed process involved. The photonic band gap structures, it controls the automatic wave propagation and enable efficient frequency selectivity. Grating structures enable efficient light coupling, enhancing radiation patterns and providing tunability for specific terahertz frequency. Dielectric substrate, enhancing impedance matching, reducing reflection losses, shaping radiation patterns, and enabling customization for specific applications. Slot coupling, enable efficient energy transfer between the antenna and surrounding medium. Antenna arrays, providing beam forming capabilities and increased gain and spatial diversity. Frequency selective surfaces, selectively filtering frequency, enhancing bandwidth, reducing interference, and allowing for customized antenna characteristics. Tapered slot antennas, facilitating efficient radiation, and improved impedance matching, optimizing signal transmission and reception in terahertz frequency range, near field coupling, enabling efficient energy transfer, compact design, and improved radiation efficiency for stronger signals and versatile configuration. Split ring resonator, introducing metamaterial properties, allowing manipulation of electromagnetic waves, improving bandwidth and increased efficiency. The research gap in terahertz antenna, the literature survey reveals three vital areas that have not been adequately addressed in existing studies. Initially, the innovative designs for microstrip patch antenna need to be developed meticulously optimized for terahertz wireless communication, considering specific substrate and patch materials for efficient terahertz range of operation. So, based on material selection, we have proposed our research for terahertz antenna design. Then, integration of frequency selective surfaces with microstrip patch antennas for terahertz communication and their potential impact on performance is found to be an unexplored area. Finally, the modeling of microwave MIMO antenna array for future terahertz wireless networks is in the initial stage. So, objectives of 6G network research, we have done our research based on the three key parameters here we listed. We have designed a terahertz antenna based on material selection, and we have designed our terahertz antenna by using a frequency selective surface, and we have designed an antenna by using a split ring resonator. For the first methodology, we have used the antenna frequency of 0.3 terahertz. For the second methodology of antenna with frequency selective surface, we used the frequency range of 1.5 terahertz. For the split ring resonator, we have used the frequency range of 1 terahertz. The first methodology, the analysis of substrate and patch materials for terahertz antenna. The aim is to analyze the suitable materials that can effectively operate at terahertz frequencies, considering the factors such as return loss, VSWR, voltage standing wave ratio, and bandwidth and gain. Next methodology, implementing frequency selective surface substrate on patch antenna for terahertz communication. The objective is to study the effects of FFSs on antenna performance and investigates its potential for enhancing terahertz communication system. And third one, modeling of split ring resonator loaded terahertz antenna array. The goal was to explore the feasibility of using metastructures to enable future wireless networks with improved performance in terahertz communication. The analysis of substrate and patch materials for terahertz antenna. In our proposed research work, what we have done, where we selected an antenna dimension of 400 across 1 micrometer, and presented with different substrate and patch material. We have used the patch dimension of 252.4 into 252.4 micrometer square, and the length and width and height of feed are 0.2 mm, 0.01 mm, and 0.000 mm respectively as shown. The research aimed to investigate the performance of microstrip patch antenna with three distinct patch materials. Here we have used our patch radiating material. We have selected three different patch radiating materials. They are namely copper, gold, and graphene, and four different substrate materials at a frequency of 300 gigahertz. We have done this simulation using high frequency structural simulator. So this is our proposed antenna design with the given dimensions of patch and substrate and feed network. We observe that we have used three patch antenna radiating material: copper, graphene, and gold. For that, we have listed out the graph for return loss and VSWR, and the radiation characteristics of proposed terahertz antenna with respect to the material selected, that is gold, graphene, and copper. So we have done our research
Which
with that.
one?
Here we have the
You
simulation.
have one.
Here we have the simulation outcomes for with respect to our patch antenna materials. So with based on we have selected three different patch antenna radiating material, that is copper and graphene and gold. For that we have listed out the inferences based on our simulation results. So dielectric constant for copper it is 6 and graphene 6.9, and for gold it is 6.9. And for resonating frequency 300 gigahertz for copper and 299, and 300 gigahertz for gold, and return loss in dB minus 26 dB and minus 20 dB, minus 26 dB for copper, and minus 20 dB for graphene, and minus 20 dB for gold. And VSWR, it is zero point 0.8 for copper, and 1.6 for graphene, and 1.7 for gold. Radiation efficiency for copper it is 98, and for graphene 99.4, and for gold it is 100%. Bandwidth in terms of gigahertz, it is 1.47 for copper, and graphene it is 1.49, and for gold it is 1.48. So with this, we always select radiating antenna, which gives the attributes of high dielectric constant and high efficiency, and zero return loss, and high VSWR. Based on that, we'll select the material selection of radiating patch antenna. So in this, the listed patch antenna radiating materials for terahertz communication, we based on the cost effectiveness, and based on the reduced return loss, and based on the material flexibility, and based on the cost effectiveness and antenna efficiency, we preferred in our conclusion, we have given our conclusion that graphene material will be the suitable material for using a patch antenna in based on our inference, because it is a cost wise also it will be cost optimized material selection. So we have, based on the inference of results, we have preferred graphene, and that is the material we concluded as a best material for patch antenna. And we go for substrate selection. We have used nearly 4 different materials for substrate. One is quartz, and silicon, and silicon dioxide, and silicon nitrate. And based on the parameters, return loss, and VSWR, and radiation efficiency, and bandwidth, and gain, we have listed out the inferences of stimulated graph for with respect to the 4 different substrate material. So gain of quartz substrate material it will be 4, and silicon 1, and silicon dioxide it is 4, and for silicon nitrate it is 3. Return loss, as we compare the return loss compared to the 4 different substrate, silicon it gives the minimized return loss. So we always prefer a material which will end 0 return loss. So and we should have a high VSWR, and efficiency it is nearly 100% for silicon, and bandwidth it is 1.49 gigahertz for silicon. In this listed 4 substrate material, based on the return loss and other feasibility parameters, we have selected. We have given our conclusion best material to select with our substrate is silicon. That is what we have concluded. So the performance of microstrip patch antenna at 0.3 terahertz using various patch and substrate materials. Copper exhibited the best impedance matching. Gold showed the ideal radiation efficiency, and graphene displayed a notable bandwidth. So we prefer to go with a future design of terahertz antenna. We prefer patch material as graphene and substrate material as silicon for having a better radiation efficiency and have a minimized return loss. Next one, implementation of frequency selective surface substrate on patch antenna for terahertz communication. In this work, we have designed a patch antenna in a dimension of 350 cross 400 micrometer square, printed on a silicon substrate, measuring 1000 cross 1000 micrometer square. The patch dimensions are 252.4 into 252.4 micrometer square. The length and width of and height of the feed are 0.2 mm, 0.101 mm, and 0.001 mm respectively. Initially, the band stop frequency selective surface unit element was designed, and its parameters were validated using MATLAB. Subsequently, rectangular patch antenna with FSS frequency selective surface substrate was designed by employing the desired parametric analysis. The proposed antenna was compared against the standard single patch antenna without frequency selective surface to assess its performance. So we have designed antenna, normal patch antenna, and we analyze the key parameters, antenna radiation parameters, and similarly we have designed the same patch antenna using frequency selective surface, and we analyze the radiation parameters. With that, we have inferred the upcoming points. So we here we refer that we have graphs represented with respect to reflection coefficient and transmission coefficient S11 and S12. Discussion on S11 and S12. Based on that, the frequency selective surface exhibited distinct stop bands at three frequencies, the namely 2.33 terahertz and 3.07 terahertz and 6.11 terahertz. At these stop bands, the reflection coefficient S11 values were measured to be -50, -43, -58 respectively. The negative values of S11, that is reflection coefficient, indicate that the significant portion of the incident power is being reflected away by the FSS substrate at this frequency, contributing to the selective behavior of the FSS. So frequency selective surface, its attribute is it will allow only desired frequency and it will filter the undesirable frequency. That is what here they concluded with the first paragraph. Then the transmission coefficient was S12. The transmission coefficient was observed to be -104 at 1.4 terahertz, -107 dB at 1.9 terahertz. These values represent the attenuation of the transmitter power, indicating the frequency selective surface substrate to allow specific frequency to pass through while attenuating others selectively. So the frequency selective surface, it will have filtering of few frequency and desired frequency when we allowed for desired frequency will be enabled for radiation purpose. That is the special nature of frequency selective surface. That is what we examined using this S11, S12 parameter. That is reflection coefficient and transmission coefficient parameter in terms of S11, S12. With this, we infer the FSS's nature of getting improved radiation characteristic in a narrow down bandwidth. Design of FSS frequency selective surface printed patch antenna. Here we have the dimension. Here we have tried out with a single element patch antenna and dual layer frequency selective surface printed patch antenna, and we tried with simulation, and we come arrive with a lot of inferences. Based on that, we have tabulated these values. Based on the simulation of using a normal single patch antenna and using a frequency selective surface printed substrate microstrip patch antenna, based on the inference of results, that is return loss and bandwidth and directivity and gain. We have for single patch antenna, the return loss will be -24. For frequency selective surface substrate printed antenna, it is -27. Bandwidth in terms of terahertz, it is 1.23, and for frequency selective surface, it is 2.26. Directivity, it is 7.6, and for FSSS printed antenna, it is 11.4. It shows high directivity. And gain, it is 7.93 for single patch antenna, 11.67 for FFSS printed antenna. It shows high gain compared to a normal antenna. FFSS antenna, it gives an high directivity, high gain, and bandwidth, and minimized return loss. So this shows the efficient performance attributes of frequency selective surface antennas. The summary of using normal and FSS selective surface antennas. The results showed that FSS patch antenna achieved a substantially lower return loss compared to the normal single patch antenna. Additionally, FSS integrated antenna, remarkably, it have wider bandwidth compared to the normal single patch antenna, as we discussed with respect to the metrics what we discussed in the tabulation. Further analysis revealed that FSS antenna directivity is high compared to the single patch antenna. FFS provides a high radiative gain compared to the single patch antenna. It is all these parameters we discussed in the tabulation itself. In conclusion, implementing FFS substrate and microstrip patch antennas for terahertz communication offers a promising solution to enhance the antenna performance. This is the conclusion what we derived out from our second work that we're using a frequency selective surface for a terahertz antenna, which is operating at a frequency of 1.5 terahertz, where we observed this radiation parameters of FFS antenna and a single patch antenna, where we with this inference of this is we concluded all FFS antenna outperforms compared to a single patch antenna. Then we have selected the third work, that is splitting resonator based massive MIMO antenna array modeling for terahertz network. Splitting resonator is nothing but we have to select meta material surface, meta materials which is having the permittivity value less than 1. With based on that, we'll have we can make our antenna to have a better desirable radiation future metrics. So this work focused on design and analysis of splitting resonator loaded microstrip patch antenna operating at a resonant frequency of 1 terahertz. Here, our main objective is to improve the gain and bandwidth by using splitting resonator compared to normal patch antenna. By using splitting resonator SRR, we can improve the gain and bandwidth. We by simulation results, we infer the same point. Initially using we'll do budget analysis for doing preferring a splitting resonator. We'll go for budget link analysis, and we'll do a lot of calculations in doing the antenna design. Here we have the microstrip antenna size. It is of 1000 cross 70 micrometers square, loaded with 9 cross 9 split ring resonator elements. Is designed and analyzed using HFSS. Finally, in order to improve the gain of the proposed antenna is transformed into an antenna array. So here the values with respect to the antenna design: transmit power in dBm, transmit antenna gain, carrier frequency, distance, free space path loss, receive antenna gain, system bandwidth, receiver power, noise figure, thermal noise power, SNR, signal to noise ratio, system capacity. All these variables it is used for designing a link budget equation for doing the antenna design of this split ring resonator. In this work, as for the link budget analysis of SRR loaded microstrip antenna, having the size of 1000 cross 1000 70 micrometer square is designed. The lower layer of the substrate has a thickness approximately 40 micrometer. In contrast, the upper layer where split ring resonator array is printed as a thickness of 30 micrometer. The use of split ring resonator array in the upper layer intended to enhance the antenna performance and to achieve the desired terahertz frequency operation. Here we have the metrics with respect to split ring resonator antenna array. We will compare the single patch antenna performance. So yeah, design of split ring resonator loaded patch antenna. Here single we have represented a single patch antenna design, and split ring resonator loaded patch antenna design. Here we already given you the dimensions. So the parameters, length of the patch, for the geometrical configuration of the terahertz patch antenna with SRR load. Here the parameters are given with respect to SRR design of split ring resonator microstrip patch antenna design. For the parameter values are given here. The length of the patch is 350 micrometer, width of the patch 400 micrometer, length of substrate 1000, width of the substrate 1000, length of split 4 micrometer, inter element spacing 10 micrometer, width of the conducting strip 5 micrometer, length of the conducting strip 80 micrometer. Return loss plot of single element patch antenna and frequency. Sorry, here we have SRR loaded patch antenna. So here we have the observed value of return loss. Always the SRR loaded patch antenna proves it is of very less waste. It shows a minimized return loss as compared to the normal single element patch antenna. And radiation attributes, the directivity, gain also, it provides a much narrower bandwidth compared to the normal single patch antenna. The SRR provides a narrower bandwidth and high directivity gain and narrower bandwidth. So with that, it proves which we can have high gain with respect to single element patch antenna. We can, in SRR loaded patch antenna, we can have a high radiation efficiency, high directive gain. That is what we can infer from this radiation pattern diagram. So here are the simulation parameters with respect to single patch antenna and SRR loaded printed patch antenna. Return loss, it is minus 48 for SRR loaded antenna, minus 30 for dual band antenna, it is minus 38, minus 34. And bandwidth, it is 5 gigahertz. SRR loaded antenna bandwidth 61 gigahertz, 51 gigahertz, and directivity 7.72. And we'll have in SRR we have high directivity 10, and gain we'll have 7.99. And for the SRR loaded antenna we'll have high directive gain. So based on the inference, what we received from the simulated graph, we have tabulated these values. So the antenna array analysis, the gain of the proposed SRR loaded antenna is 10.66 dBA, which is sufficient to meet the link budget requirement. In order to improve the gain, the proposed dual SRR loaded antenna is transformed into an array while using uniform linear array arrangement with an antenna elements of n equal to 200. The proposed antenna array exhibits a gain of 21.95 dBA. The uniform planar array arrangement of n equal to 12 cross 12, the antenna array exhibits a gain of 20.54 dBA. Additionally, the antenna array offers high gain steering capabilities of approximately plus or minus 15%. Here we represented the uniform planar array analysis and the radiation pattern, and uniform linear array analysis with respect to n equal to 200 elements. And we listed the proposed antenna designs, gain and size. And here in the below we listed various reference papers wherein which the lot of researchers did and research, and based on their operating frequency, what the gain and bandwidth they derived, that is listed out. And we compared the previous authored papers. We have compared with our own paper, own research work. With that, we designed this particular table. And operating frequency of ours, it will be 0.9 to 1 terahertz, and gain it is 10.6, and bandwidth it is 11.8 percentage. We have bandwidth improvement, it is of 11.8 percentage. It is the inference we received through our third research work. The summary of the third research work: the SRR antenna exhibit dual mode operation with broader bandwidth and of 51 gigahertz and 61 gigahertz compared to 5 gigahertz for the single patch antenna. It also shows higher directivity of 10.40 dBA and 7.72 dBA, and higher gain of 10.66 dBA versus 7.9 dBA. While using a uniform linear array arrangement with a number of antenna elements n equal to 100, the proposed antenna array exhibits a gain of 21.95 dBA. In uniform planar array arrangement of n equal to 12 cross 12, the antenna array exhibits a gain of 20.54 dBA. Additionally, the antenna array offers a high beam steering capabilities, approximately plus or minus 15. And use cases and applications of 6G. 6G can be used in enhanced mobile broadband, high speed internet access for mobile users, ultra reliable low latency communication, URLC applications requiring extremely low latency, such as autonomous vehicle and remote surgery, where we can in future we can use 6G. Massive machine type communication, IoT application with massive numbers of devices, like smart cities environment, we can use 6G networks. Research and development in 6G. Current research areas are advanced antenna technology in terms of beam steering, holograph beam steering, just before we discussed, that is the latest we are using. AI driven network management. Using AI we can have a better network management, and we can improve the network performance. New types of beam steering waveforms, and that can be a future research. Future direction: integration with satellite networks and quantum communication. These are the upcoming developments in 6G future era. So conclusion: worldwide cellular phones, in 3G it is operator centric, 4G it is service centric, 5G it is user centric, and 6G technology is user centric and service centric. 6G technology is in the development stage, as this is an ambient technology which can boom the latest era, which it's splendidly well application. Frequency range shows our vibrant pod and our expectation. At last we can say it is all about blink and think. That is what in upcoming 6G research we'll have a lot of various dynamic metrics, we can go with different research. Even in our research, we have selected only three key parameters: material selection, and we have done using material selection. We have designed our terahertz antenna, and we have come arrive with some inferences. That is what we discussed today, and we have selected frequency selective surface, and with based on that we have derived our inferences, and we have selected designed an SRR printed antenna. With that we have derived our inferences. So upcoming researchers, they can go with all these parameters, and they can extend their research, and they can derive a lot of research based metric papers. So in this 10 parameters, we have selected material selection, the point number 1, and the 7th point frequency selective surface based antenna we design, and we derive some inferences. And 10th one, the split ring resonator. Based on this three parameter, we have done our extended research, and we derived our publications. So the future researchers, they may try with all the other scopes of parametrics, and they can derive the research for upcoming 6G improvement in technology. This is all about our research we carried out recently. Actually, one of my research scholar, Mr. Selva Kumar, has done this research, and with his research work, we facilitated our delivery today. Conclusion: importance of addressing spectrum scarcity for the success of 6G, the need of innovation, technology, and regulation, the potential impact of 6G on industries and everyday life. So these are the major conclusions we defined doing the research. Thank you all for your. These are the research papers we referred in doing while carry out our research.